Alright, we're still in unit number 6. My last video, if you watched the last video, I was in the process of working through the video, and I had a student knock on the door, and this particular program that I'm using to do the recordings doesn't allow me to pause. So instead of going back and redoing the entire video, I'm just going to pick up where I left off on the previous video, and I think we're in part H. Alright, so the question is what is the net power? We're going to calculate the net power in two different ways. We're going to use the equation that you'll use most often. We'll use this one. And then in method number 2, we're going to use the one that's a little bit more sophisticated, but you'll catch on to it fairly quickly. Alright, so we want the net power. So if we want the net power, then we need to have the net work. So let's go ahead and figure that out real quick. Figure out what the net work is, and then we'll get the net power from that. So remember that we had, well, let's go back over here to our diagram from the previous video. We had basically three forces. We had the normal force, we had the force of friction, and we had the weight. Remember, we don't really consider these two forces because this weight is really the sum of those two forces. So just a heads up on that. All right, so if our movement is this way, then the normal force is not doing any work because the motion and the force are parallel. However, this guy is doing work and the weight is doing work. So we need to go find how much work did the force of friction do, and how much work did gravity do. And we did gravity in part B or in part C. So gravity did 3,430 joules. So let's just kind of write that down over here. So we'll kind of keep a list of it. So work done by gravity was 3,430 joules. And then, what else did we say? We said friction did work as well. So let's go find friction, and we did that in part G. In part G, friction did, let's see, write that down here. Negative 3,430 joules. And so if we add those up, that'll be the net work, and that's 0 joules. Ooh. What's going on here? So the net power is equal to 0 joules divided by whatever time. Well, that's going to give us 0 watts. What does it mean that there was no net power done? Well, let's go back up to gravity real quick. What does it mean that 3,430 joules of work was done? Well, it means that 3,430 joules of energy was given to the box. You could think of it as given to the box to cause the box to speed up. But also remember this, friction did negative 3,430 joules. What does it mean that friction did negative 3,430 joules? Well, it means that 3,430 joules were taken away from the box. That would cause it to slow down. So you have two things doing work. One's causing it to speed up, the other's causing it to slow down, and they're doing it in equal values, just opposites. And so you could say that, well, if 3,430 joules are causing it to speed up and 3,430 joules are causing it to slow down, and they're equal, then that means the object is moving at a constant speed. And if we look back here to the original question, right there, constant velocity. So it does kind of make sense that this is moving at a constant velocity because we have equal amounts of energy entering the system and exiting the system. So it should be 0 watts there. Let's see what happens over here. So we need, if we want the net power, we need to also have the net force. Well, what was that net force? Let's see if we can go find that. I think that was in part E on the previous page. And the net force right here. Bam. 0 newtons right there. So 0 newtons. Let's see if we can kind of spread this out a little bit. Open up the dot product. So we got net cosine power 0 newtons times V times cosine theta. I don't even have to worry about plugging those numbers in because it's going to be 0. And that'll be 0 watts. So it kind of works out kind of nice like that. All right, part I. What is the power generated by gravity in watts and horsepowers? Now, you got to remember, in the previous example, we did the power generated net. That we just calculated the net power. We're not looking for net power on letter I. We're looking for the power generated by gravity. That's a little bit different. All right, so let's go ahead and we're going to use two methods, two equations. So we'll do the first one, kind of the long way, but you need to see it done. So power is force dot V. Since we want gravity, we need to have the force of gravity into there. So let's go ahead and throw that in here. So this is going to be force of gravity V cosine theta. So that's weight, and weight is really going to be mg V cosine theta. All right, let's plug these in. Let's see what we get. The mass of the object. The mass of the object, I think, was right here. It was 70 kilograms from the first page. The acceleration of gravity is 9.8. And remember, at this point in time, we don't need the negative because we had vectors here. But as soon as you operate or do the dot product, the vectors go away. And so we don't need to worry about the negative there. All right, the speed. Let's see, what was the speed? Let's look backwards and let's see if we can figure that out. Did they give us a speed? Well, it went 10 meters in 20 seconds at a constant velocity. So 10 meters in 20 seconds, that'll be basically half a meter per second. So come back over here. So half of a meter per second times cosine. Now what is this angle? Well, let's work this backwards. That angle is going to be the angle between the F and the V. So let's just go ahead and go back to our page. Alright, so the F and the V, well, the force is the weight, and the weight is down. And the movement is to the right, down the plane. So we want the angle between them, and in the previous video I think we figured out that that was a 60-degree angle right in there. Alright, let's go ahead and plug this in and see what we get. So 70 times 9.8 times 0.5, and then cosine 60. Make sure your calculator's in degrees. And then we get 171.5, and that'll be watts. So gravity is doing some work, and it's doing 171.5 watts. I said that wrong. Gravity is doing exerting some power, and the power it's exerting is 171.5 watts. Okay, the next equation. Power's work over time. This is the one you probably use most often. So if we want the power generated by gravity, we have to use the work done by gravity. And I think we've done that, and we've calculated that. If we go back to part C on the first page, this guy right here, 3,430 joules, was the amount of work done by gravity. So I can go ahead and plug that in. 3,430 joules divided by the time. Let's go back over here, and I think the time was 20 seconds. And then we can divide those out. So 3,430 divided by 20, and we get, hey, we get the same thing. And we should get the same thing because they did the same amount of power's measured in watts, not joules. So they did the same thing, so that makes sense. They should be doing the same thing. Alright, now let's go to the next one. All else being the same, if the object slides down the ramp in a shorter amount of time, the power generated by gravity will, well, let's look at the equation here. Power is work divided by time. If you go down in a shorter amount of time, then the power should increase. Because you're doing the same amount of work, but you're doing it quicker. And if you do it quicker, then your power will increase. And that's the video. Next video, we're going to work through work energy theorem.